At this point, we are very comfortable thinking in rectangular coordinates or Cartesian coordinates in three-dimensional space. And we've now added the idea of cylindrical coordinates, but there's one more type of coordinate system that we're really going to want to study, and that's called spherical coordinates. And here's how spherical coordinates of a point are defined. So let's say we have a point P here. We know how the rectangular coordinates work. I'll sketch the little picture here. But the idea is that in rectangular coordinates, this point has an x value. It has a y value, so this gets us over to some point that's supposed to be directly below the point P in the z direction. And then the last component of this point, so this green line here, this has a length of whatever we call the y component. And then the final component here is the z component. Okay, and so this point lives on the diagonal, so it finishes off the diagonal of a rectangular prism for which one corner is the origin and the other corner is the point P. And so this point P is described by these coordinates, x, y, z. But of course, this is not the only way to describe this point. So this point, again, this is called rectangular coordinates because we think of this point as lying on the opposite diagonal of a rectangular prism from the origin. But there, like I said, there are many other ways to think of or how to describe this point, and different ways to describe this point. And one of the most useful ways is to think of this point as lying on the surface of a sphere that is centered at the origin. So I'm going to try to sketch a sphere that is centered at the origin. So this is supposed to be a sphere centered at the origin. And the idea is that this point lies on the surface of the sphere. And if this is the case, then one of the pieces of information that we need to describe this point is the distance from the origin to the point. And so this length is going to be called rho. This is the radius of our sphere. So here, this is a Greek letter rho. It looks kind of like a P or an E. It's actually the Greek letter for R. It's rho. But this is the radius of the sphere. And of course, the radius of the sphere is the distance from the point P to the origin. And so we can just write down, well, rho better be, rho squared, sorry, should better be equal to x squared plus y squared plus z squared. This is the equation of the sphere that this point lies on. Then there are two other pieces of information that we need to describe this point P. So the radius itself is not enough. And those two other pieces of information are going to be, so this point here lives on the sphere. So the first piece of information is going to be the angle that the radius makes, this radius rho makes, with the positive z-axis. So this angle is called phi. And by convention, this angle phi is always opening downward from the positive z-axis up here. So this angle, it's this angle right here, this angle phi. All right, so phi is an angle, and this angle opens downward. All right, the other piece of information that we need is going to be another angle, and this angle is going to be the angle of rotation in the xy plane. So it's going to be this angle right here, the angle theta. We'll call that theta. That angle is called theta because that angle is exactly the angle that we would think of in polar coordinates. So this is the angle in the xy plane. And phi can be thought of, so that's an angle of rotation in the xy plane. Phi can be thought of as the angle of rotation in the xz plane. And we're going to want to think of it in this order, where we first go out, say, the positive z-axis, rho units. Then we rotate down in the xz plane. We rotate downward in the angle phi. And then from that point, we rotate around the sphere by the angle theta. So as I write this here, that this is the angle in the xz plane, that's exactly how we're going to want to think of this. Okay, really we should think of it in the zx plane because it starts at the z-axis and opens downward. Let's actually write it that way to avoid confusion later. All right, but at this point we need to try to find a way to represent this the Cartesian coordinates, x, y, and z, in terms of these three coordinates. So the coordinates of this point P, these spherical coordinates, are going to be rho, phi, and theta. Again, in this order. So rho, phi, theta. But we need a way to convert from rho, phi, theta to x, y, z. That's going to be our coordinate transformation. So really we just need equations that relate these things. So let's work them out. One thing we see here is that in the, well, there's a couple things we need to do here. So x and y, the x and y coordinates are related to the polar coordinates down here. So let's call it, we have rho representing the orange length here, the radius of the sphere itself. Let's let r represent the usual radius. So r here is the polar coordinates of the point in the xy plane that sits directly below P. So this point r, this is just going to be x squared plus y squared square root. So r squared is equal to x squared plus y squared, the usual polar coordinate of the point here. Okay? So at this point, we can now try to work out some formulas for these things. First of all, z is equal to, so this is a right triangle. So this is a right triangle here. We can see that rho, z, and r create this angle here. And if this angle is phi, then that means that this angle is phi. And so we can use just right triangle trig to write down a formula for z here. And we can do the same thing for r in terms of rho, because we're going to want to get everything in terms of rho. So let's write this down. So first of all, from this equation, we see that the cosine of phi is equal to z over rho. So the cosine of the angle phi is adjacent over hypotenuse. So this is z over rho. Remember, we're assuming that we know phi and we know rho. And so this gives us an equation that z is equal to rho times cosine of phi. So there's an equation for the z coordinate of our point. Like we said down here, we have polar coordinates for these points. So x and y. So just by polar coordinates, x is equal to r cosine theta, and y is equal to r times sine of theta. But the problem with this, and you know, this is fine, except the missing piece is that we don't know r, we know rho, right? So we need to try to get rho in here for r somehow. And we can go back to this triangle and we can notice, okay, well, if this is the angle phi, then r is the side length that is opposite of phi. And so we can get that in terms of rho the same way we did for z, except we need to use sine instead of cosine. And so here we get, all right, just looking at this, the sine of phi is equal to r over rho. And just like we did with the z coordinate, we can solve this for r. So this tells us then that r is equal to rho times sine of phi. And at this point, these are the coordinates we know. We plug those back in for the r here, and we can write down our transformation. Y is going to be equal to, I'm working backwards here so that we can have a nice formula when we're done. But if we plug in rho sine of phi for this r, we end up with rho times sine of phi times sine of theta. Notice these are both sines, but they're different angles here. And the x-coordinate is rho times sine of phi times cosine of theta. All right, and so this is the coordinate transformation. If we know the spherical coordinates, we can get back the x, y, z coordinates. And this is the way we're going to use this when we integrate. So this is the transformation that we really care about. And again, the idea is that to build a point on the plane, or on the sphere, we, in our minds, we travel out the z-axis first, travel out the z-axis to the length of rho, then we rotate down in the xz plane, the zx plane, by this angle phi, and then and only then we rotate around this angle to get over to this point, so that's theta. So the correct order is rho, then phi, then theta, at least in the way that we're constructing these. And this is, when I say it's the correct order, I mean it's the order that we are going to agree to all do the same way, so that when it comes time to integrate, we're all thinking in the same sense. So it's a convention that I'm setting, but I'm setting it for all of us. So.